Okay, so in this video we're going to take a look at some conservation of momentum type problems. So we've got a 20 kilogram comet traveling at 10 kilometers per second. Okay, so let's do that. So we've got 20 kilogram going at 10 kilometers per second, so that's 10,000 meters per second, collides with a 500 kilogram satellite going in the opposite direction at 220, and then what that's going to end up as is it asks you for their combined velocity, so we're going to model them as being combined together, so maybe they've smashed into each other and melded and stuff. And what we're going to try and work out is essentially what speed is it now, or what velocity is it now travelling at. So we do that is the momentum initially is mass times by 10,000, and then it's going to be minus 500 times 220, and the reason for that is direction is important with momentum. So if it's in the opposite direction, it's going to have negative momentum. So what we've got here is, if we calculate that, we're going to end up with 9.0 times 10 to the 4. So we look at the momentum, finally it's going to be 520 times whatever the velocity is, and we know using conservation of momentum those two have to be equal to each other. So what we can do from that, we can essentially say that the final velocity, or x in this case, is going to be the initial momentum divided by the mass, and that's going to give us 1.7 times 10 to the 2 meters per second. And you might be wondering why I've given that in standard form. Well, if you look at the data we used in the question, we've got a 2 significant figure number here, so that means our answer is going to be for 2 significant figures, and the way we do that is by using standard form. Okay, so let's move on to the extra practice question. So we've got a 400-ton asteroid heading towards the Earth at a relative velocity of 5 kilometers per second. So we've got these. We know this is 400 tons. And we know it's heading at 5 kilometers per second, like that. And if we look it up, we've got the mass of the Earth, 6.02, blah, 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 blah. And it says we're going to model it as being stationary. And then what we're going to end up with is the two objects combined together. So we add the masses together, and now that's going to be travelling at a velocity of v. So the initial momentum is just going to be 4.00 times 10 to the 5, which is the mass of the asteroid, times by 5,000. And if we put those together, we end up with an initial momentum of 2.0 times 10 to the, blimey, 1, 2, 3, 4, 5, 6, 7, 8, 9 Newton seconds. You know, the final momentum is going to be the combined velocity times by their combined mass. So that's like 400 tons. So essentially what we can do is we can find the velocity is going to be 2.09 10 to the 9 divided by 6.02 times 10 to the 24 plus 4.00 times 10 to the 5. And if we put those numbers in, I don't know where the 9 came from there. Let's get rid of that utter rubbish. So 2 times 10 to the power of 9 divided by 6.02 times 10 to the 24 plus 4 times 10 to the power of 5. We end up with B is equal to 3.32 times 10 to the minus 16. 16 meters per second. There. You might be thinking that's really small, but you would kind of hope that the Earth wouldn't move too much if it got hit by asteroids, because otherwise we'd get knocked out of our rotation all the time every time we got hit by an asteroid. So you would expect a very minor change as a result of a collision with an asteroid, so that seems reasonable. Okay, so let's move on to question on space dodgems. So we've got a 10-ton shuttle fires a 400-kilogram rocket at 200 meters per second to the left when it was traveling at 1,000 meters per second to the right, and then that's then going to collide with something. So let's solve the first stage first of all. So initially, we're going to have a rocket plus a shuttle, so 10.4 tons, and it tells you is going at 1,000. And what that transfers into is our 400 kilogram rocket going at 200 to the left, and we've got our 10-ton shuttle travelling at V. So if the total momentum is the same, we can sort of see that V is going to be greater than 1,000 here, but let's work through it. So we've got our mass in kilograms times the velocity again in meters per second. So it's going to be 1.04 times 10 to the 7. That's going to be essentially the initial momentum. Final momentum is going to be minus 400 times 200 plus 1 times 10 to the 4 V. That's your 10 tons. So the total momentum of the 10-ton shuttle is going to be the addition of those two numbers. So 1.04 times 10 to the power of 7 plus 400 times 200 which is 1.048 times 10 to the, how many was that, 1, 2, 3, 7 Newton seconds. So that's the total momentum of the 10-ton shuttle. So then it says this shuttle is going to collide with a stationary 12-ton shuttle. So in that collision, we know the initial momentum is this 1.048 times 10 to the 7 Newton seconds, which is why I didn't bother calculating the velocity before, because I knew I was going to need the momentum later on anyway. The final momentum is going to be the sum of the two masses, so 2.2 times 10 to the 4. That's the 12-ton shuttle plus the 10-kilogram shuttle, and it's going to be multiplied by their combined velocity, and so then we can essentially solve this by doing our total momentum, and then we're going to divide that by the total mass of the two objects. And once we do that, let's type that in. So our answer divided by 2 times 10 to the power of 4 gives us 476.36 blah blah blah. So it's going to be 4.8 times 10 to the 2 meters per second there, giving it to two significant figures, which would be appropriate because we've got 12 tons and 10 tons, that kind of thing. Okay, so moving on to the final question I'm going to look at. So we've got an 8-ton shuttle is being used to launch a nuclear missile. The shuttle launches a 200 kilogram missile at 150 meters per second to the left, followed by another of the same mass going at 180 meters per second to the right. Calculate the velocity of the shuttle afterwards. So first of all, the initial momentum is assumed. You're not given any information, so we're just going to assume it is stationary. The final momentum would therefore also have to equal this, but we're going to calculate it, so it's going to be minus 200 times 150 plus 200 times 180 plus 8 times 10 to the 3, so these are 8 times your velocity. We know that the initial momentum is going to equal the final momentum. So what we can do is we can do some rearranging. So we've got the mass of the shuttle times the velocity is going to be 200, 150 minus 180, which is equal to minus 6,000. So we can calculate V is going to be minus 6,000 divided by, that's 8,000. 6,000 divided by 8, that's going to be 3/4. So that's going to be minus 0.75 meters per second. So that's going to be 0.75 to the left, essentially, there, once you've calculated it. And that concludes the questions I'm going to look at in this video.